All right, welcome to College Algebra. Um, in this course, we're going to cover parts of Chapter 3, or we're going to start in Chapter 3, go on to Chapter 4, we're going to jump over Chapter 5, and then we're going to finish off with a little bit of Chapter 6. So, to start with just a little review, we're going to do the other common functions section as just kind of a nice review on what are some functions that you're going to run into, and namely we're going to look at how does the exponent affect these different functions, and then we're going to talk a little bit about, well, what happens if you stick a number out in front, what happens if the number is greater than 1, less than 1, what if it's negative and meets those. So we'll be going over just a couple of things like that. So notice the main topic, like I said, we were looking at, it was going to be powers of, or I guess the best way to put it is we're looking at powers of x. So a times x to the n, a over x to the n, which you may be more familiar as x to the negative n, and then a times x to the 1 over n. This one also you may be familiar as the nth root of x. So just a couple of different functions. These are the most used. These are the ones that we're probably going to have to deal with the most. So just reviewing them kind of helps get that fresh in your mind and make a good start off to the semester. So functions of the form ax to the n, notice if we start out with x to the first, x cubed, and x to the fifth, they stay, well, I shouldn't say they stay pretty much the same. Once you get past x to the first, the shape is pretty much the same. Now, all of these have, we're letting a be equal to 1 just for the sake of sanity and to make it a little bit easier. But x to the first is just a line. X to the third is this cubic function. And then x to the fifth still keeps that cubic shape, where you notice the main difference is because the power is much higher. If I were to do 2 cubed, I get 8. But if I do 2 to the fifth, then I get 32. So it's already just taking these values and just making them so much larger. Like, even if you did 3 cubed would be 27, and then I think 3 to the fifth, I'm not going to try and do that one off the top of my head. But the key thing, and we're going to talk about, these are going to come up, your domain for all of these. So this one we would say n is odd. And one thing that I didn't state that's just kind of going to be understood, we're mainly going to deal with n as a whole number. And what I mean by that is, like, we're not going to let n be 1/2 or 33 over 7, something like that. We just want to stick with integers. Part of the reason also, if I go back one, that we don't do like negative 1/2 or like do 1/2. Notice if I did that, if I put like 1 over 1/2, this would just revert back to 2. So it would just throw it back into that one. So that's part of the reason why we're sticking with that. And then if you have like fractions that don't have 1 as a numerator, then it gets a little bit messier. So we're just going to keep it like this for now. But the domain of these is negative infinity to positive infinity. The second one turned out a lot better than the first one. Let me see if I can fix that. No, but it's a little bit better. And the range is also negative infinity to positive infinity. So domain, this is associated, just as a review, domain, this is associated with your x value. or x values. If there's an infinite number of them, I'm assuming that it's more than one. And then the range is associated with the y values. But what this is saying is for a cubic function, or sorry, a times x to the n function, where n is a odd integer, I can take that function and I can automatically know I can plug in any x value and I'll be able to get any y value. Because remember, domain, or to reemphasize, domain is what you plug in, range is what you get out when you plug in. So domain is your input, range is your output. So like if I do f of 3, and let's say I'm in using this one. So if f of x equals x cubed, then I would plug that in and I would get 3 cubed, which is 27. So this came from the domain, and this came from the range. Input, output. Now, if you want to, there's another way to write negative infinity to infinity. And it's this, I just hear people call it a fancy R. It's just this double line R. And this is the same as saying all real numbers. So you have some options. Now, typically most like input systems for like computer grading, it's typically going to want the interval. If it says interval notation, then it's referring to this. This is an interval. This is an interval from negative infinity to positive infinity. So that's just one thing to keep in mind. Because if it says what's the domain and you type all real numbers, it may not be prepared to take that as an answer. Typically it's going to specify like write as an ordered pair. So in terms of probably what you would use the most, it would go negative infinity to infinity, all real numbers, or the symbol for all real numbers, and then the words. Now, what if we make n even? Then you notice almost immediately there's a big change. Specifically, if you were to think about this as being kind of like split down the middle, this is actually symmetrical, all three of them, on the left and the right. So even functions, this is what you would refer to kind of as the more common parabola shape. These technically would also be parabolas, but typically when people think of a parabola, they go to this kind of U that's opening upward. So typically when we deal with these, we're just thinking about, okay, parabola is just going to open up or down. We'll get to that. But key takeaway is the domain previously was all real numbers. That doesn't change here because I can still plug in any number. But now notice there's a difference. My range, however, I can't get any values that are negative. If I go back, there is a point eventually where I can get, I don't know, negative 213. I can get negative 1. I know that I just got to plug in negative 1. I could get negative 8. I just got to plug in negative 2. But with the even powers, I'm out of luck. I can't get any values that are negative. So these all go down to 0. So we say that their range is from 0 to infinity. And again, we're assuming that a is equal to 1 for these. Now, the difference between the bracket and the open parentheses, or parenthesis, however you want to say it, this bracket means include the value. So if you have a interval and it's got a bracket on one end and a open parenthesis, I'm going to keep screwing this up, but whatever, open parenthesis on the other end, then it means that the bracket side, you include that value. So like in this case, I could say this because what do I need to get 0? If I square 0, I get 0. So it's included. But notice if I try and get x squared equal to -1, you get imaginary numbers, so that's not included. So bracket means include, parentheses means exclude. So if it was a number, what it could say is like, so like if you had, let's just say we had 1 that was bracketed and then 3 that was a parenthesis. If we drew a number line, so we'll do 0, 1, 2, 3, 4, just so we have some room. I'll use a different color. So 1 is included, so this is what you would think of as when you would do like the filled in dot. And because 3 is excluded, and let me remove that just random little dot from above it so it doesn't look like anything special going on, you would use the open circle to represent that it's not included. And so then like if you think of the interval, it's all the values between 1 and 3, and you're excluding 3 but including 1. So this means like 2.999 and a bunch of other 9s is included. I could have 2.1 billion 9s. That's in there because that's still less than 3. But as soon as I try and say, oh, I want to include 3, I can't just because of that value. So just kind of a little reminder on that. Now, one thing to keep in mind is what happens if we kind of play around with these values. So remember our previous one, let's identify first for A. What is n equal to? Well, n is our exponent and it's equal to 4. What's A equal to? Well, x to the 4th over 5 is like having 1/5 times x to the 4th. So our A value is 1/5. So think about what that's going to do to that shape. So typically what you would do to sketch a graph is, let's just take a few values. So if I plug in 0, I still get 0. That's pretty easy. If I plug in 1, well, I get 1/5. So here's 1, and this is a little bit smaller, so we'll try and do that. Something along those lines. Now, if I wanted to, then I could use, let's go with -1 as well. That's still going to give me 1/5 because it doesn't matter if I raise -1 to the 4th power. It's still -1. So that's just over here on this side. And again, I'm not going to be able to get these perfect, but I can still get them kind of close. So then if I do 2, let's go with 2. We're just trying to get some values. And we're also trying to not throw this thing too far off. So 2 to the 4th would be 16, and divide that by 5. So 16 divided by 5 is 3.2. And then also same thing for if I plugged in -2. So what's going on here? So if I do 2, I'm at 3.2. So here's 1, 2, 3, and some change. Same idea. 1, 2, 3, and some change. Now, one thing I'm kind of doing is I'm trying to just get a few values to get the general shape. And I'm picking nice values because as soon as I go over to 3, 3 to the 4th is 81. And let's see, 81 divided by 5 is like 8.2, I think. Sorry, 16.2. That's why I double checked. And if you notice, this is not even going to have, if I go over to 3, I don't even have enough to graph that on here. So I can't even get 16.2 on here. But I have kind of a general idea, so it's kind of going to go like this, something like that. And it's going to kind of go like this, something like that. Now it should be symmetrical. Again, I'm drawing this on a computer, on a touchscreen laptop, on a stand, so it's not going to work out as nice. Now, when a is not equal to 1, which is the case we have here, the previous functions are kind of what we would refer to as parent functions. If you've heard that term before, it's kind of just what's the general shape. Everything here and here, these are the parent functions. And anything with a different a value is derivative of that parent function. And you can notice, let's say I wanted to plot, I'll use orange. If I wanted to plot the original parent function. So then I know these values. And then, so that's 3, 4, 5, 6, 7, 8. And so by multiplying it by a fraction, and I'm going to say specifically a fraction that was between 0 and 1, it actually stretched out the function because the orange is the original. So notice it's kind of widened that original function. And so if you multiply by a number between 0 and 1, that's actually widening the parabola. If you multiply it by a number greater than 1, you actually narrow the parabola because you make it it's kind of like giving it a little bit more acceleration. Because if the original one is x to the 4th and you throw a 3 out in front of it, well, now 3 times x to the 4th, that's just going to make it go to other values a lot faster. So that's kind of one thing to keep in mind. Now, so if you multiply by a number between 0 and 1, that's actually going to widen the graph. If you multiply by a number greater than 1, that's going to actually shrink the graph. So, yeah, where do I want to make that note? Let me move this line over. So a is greater than 1. That's actually going to shrink. But if a is between 0 and 1, that's going to stretch. Now, what if you throw a negative out in front? So you can probably kind of see where this one's going to go. I'm not going to go into as much detail about it because its effect is not as, I won't say not as interesting, but it's a little bit easier to grasp from just the idea if you threw a negative out front. So think about that. If you throw a negative out front, what's going to happen? Everything that was plus is going to become minus. Everything that was minus is going to become plus. So if you plug in your values, so 0, 0 still doesn't change. 0 is still 0. But now if I throw in negative 1, well, negative 1 cubed, if I just cube negative 1, I get negative 1. But because there's a negative out front, now I get positive 1. Same idea, but flip-flop. I plug in 1. If I cube 1, I get 1. But there's a negative out front, so now I have negative 1. Same thing with 2. 2 cubed is 8, but there's a negative out front, so it's negative 8. So 2, 3, 4, 5, 6, 7, 8. And then negative 2. Negative 2 cubed would be negative 8. There's a negative out front, so it's positive 8. And thus, 1, 2, 3, 4, 5, 6, 7. I think I'm just counting. 1, 2, 3, 4, 6, 7, 8. There we go. And thus, it just kind of does something like that. And then does like that. So if you were to compare this to the original one, this middle one here, x cubed, notice that all that's happened is it's like if you took the x-axis and just turned it. And then so basically, like, imagine the x-axis is just like a bar, and like y is like the y-axis is where this, I don't know, frame or mirror is resting, and then you can just flip the thing over, and so then it just changes. It swaps your values. It swaps it over the x-axis. And to demonstrate that, so y equals x cubed. Y equals x cubed would look like this. So if a is less than 0, another way of just saying a is negative, it flips the function about the x-axis. So that's kind of your natural, or I won't say your natural, but that's kind of the way it works. You've got, if a is greater than 1, it's going to shrink the graph. If a is between 0 and 1, it's going to stretch it. And then just apply that idea with, well, what if I have like negative 1/2? Well, that means it's flipped, and it's also going to stretch it. So you can put those two ideas together, which is pretty good. Now, this is a times x to the 1 over n, or a times x to the n, which sometimes you will just see written as a times x to the negative n. And that just comes from exponent rules. Now notice what happens. This goes, again, we're using the parent function idea where a is equal to 1. So if I were to, the key thing to notice here is basically for all of these, notice you can't get 0, which makes sense. For like x cubed, x to the 5th, x squared didn't matter. In order to get 0, I had to plug in 0. So if I can't plug in 0 because you can't divide by 0, then 0 is out of not only your domain, but it's also out of your range. So, for the first line, these are x, or 1 over x, 1 over x cubed, or you can think about it as x to the negative 1, x to the negative 3. You get the idea. The domain for this one is negative infinity to 0 with a parenthesis, and then union 0 to positive infinity. So if you ever have to split up your domain, then you just do this little U. The U means union. So fortunately, this is one of the few things that mathematicians actually named appropriately. It looks like a U, it means union. Or I guess vice versa. We want it to mean union, so let's just use U. And now the range is actually the exact same thing, because notice these almost just kind of look like reflections of each other. So I can get any y value going negative, except when I try and come up to 0, and then I can get any y value that's positive. So this function shares its domain and range as being the same thing. I can plug in every value except 0, and I can get out every value except 0. And then what if the exponent's even? So you got x to the negative 2, x to the negative 4, x to the negative 6. And if you prefer to leave it as 1 over the positive number, that's fine. I'm not picky either way. I just always like to show both methods just because, or both ways of writing it, just because some people have a preference over the other. But with these, well, if we take a look at the domain, then pretty much like before, I can plug in any x value. And you can look at that here. I can plug in any x value except for 0, because I don't want to have 1 over 0. So this one has a domain of negative infinity to 0, union 0 to infinity once again. But if you look at the range, kind of like going from the odd, or it's exactly like going from the odd power to the even power. When you have the odd power, you're allowed, or not allowed, you're able to get out negative values. Because you multiply a negative number 3 times, you get back a negative. But you multiply a negative an even number of times, you get a positive. So with this one, the range is actually 0 to infinity, but 0 is excluded. So anytime you have x to the negative power, or x, or a number over x to a power, 0 is excluded from your domain. And that's in both cases. The range is going to boil down to what is going on in the... what's going on in the exponent. But it's kind of nice to remember that if you have x squared, its range is 0 to infinity, but 0 is included. If you have 1 over x squared, the range is 0 to infinity, but you can't include x, or you can't include 0, sorry. So that just makes life a little bit easier. You can keep up with things without too much hassle. Now, if you have 1 over n, or the nth root of x, there's some kind of interesting stuff that happens. Because you notice basically what's happening is you're getting, this is the cube root function. I'm kind of ignoring the first one because 1 over 1 is just 1, which we've already talked about. So 1 over x to the 1 over 1 and x to the 1, that's kind of like the only function that lives in both x to the n and x to the 1 over n. It's kind of it's the only function that's special enough to live in both of those worlds. So just kind of an interesting thing. But with these, notice your square root of x, this would be the 4th root of x, this is the 5th root of x, and the 6th root of x. Notice if it's odd, then your domain is negative infinity to infinity, and your range is also negative infinity to infinity. It just makes it nice. Because even though these numbers are climbing very slowly, they're still climbing. Eventually, I can get some number that has the cube root that's equal to 15 billion. Might take me a while to get there, but eventually I will get there. But x squared, or the square root of x, 4th root of x, stuff like that, because you can't take the square root of a negative number, they don't have anything or any values to the left of the y-axis. Because I can't come over here and go, oh, what value do I need to plug in to get negative 2? There isn't any. I mean, you can say negative 2i, or 2i, but we want to try and avoid... We're in the real plane. That's what I should say. When we're in what's referred to as Euclidean space, sometimes you'll see it written like this, R2. And what that means is we're using real numbers for the x values and real numbers for the y values. So we don't want to go through and bring in and drag in imaginary numbers for this. But your even roots, and I don't refer to these as like a 1 over nth power or a 1 over n. I typically just refer to these as a root, just because that's most of the time what you're going to experience them as. And it's easier to think about, oh, well, that looks like a cube root, or that looks like a square root, than it is to think of, that looks like x to the 1 over 2, or that looks like x to the 1 over 3. So that's the way I'm going to try and refer to them so I'm consistent. But notice both of these, they have a domain of 0 to infinity, because I can plug in any value that's equal to 0, or a positive number, because you can take the square root of any positive number. You can take the 4th root of any positive number. You just can't take the square root, cube root, even root of a negative number. I wrote domain twice. Is what happens when I try and talk and write at the same time. The range would also be 0 to infinity. Because like I said, I can't get out any negative values from anything I plug in. So that's the way that we kind of want to keep these in mind. Now the absolute value function, basically everybody knows the easiest way to think about it is if it's an absolute value function, you plug in a number. If it's negative, it just becomes positive. In reality, what the absolute value is, it's a very special piecewise function, but we typically don't talk about it as a piecewise function. We just leave it as the absolute value function. Yep. And so, pretty easy to see. If I plug in negative 2, or if I plug in 1, or a negative 1, they both come out as positive 1. Basically, all this design is designed to do is just remove the negative sign. That's all it does. Now, what if we flipped it, or I shouldn't say flipped it, spoiler alert. What if we multiplied it by negative 2? Well, go back to those ideas that I talked about beforehand. They're still going to apply here even to an absolute value function, because it's still in a family of these functions. So 2 is greater than 1. So a is equal to -2. And remember I said if a was greater than 1, that would narrow it. Now, the reason I say that is if you're looking at this going, well, this is -2. Typically, the way we tend to think about it is if it's between 0 and 1, or if it's between -1 and 0, that's going to stretch it. If it's greater than 1 or less than -1, then it's going to shrink it. But it's a little bit easier if you want to break them apart into just having to remember, okay, well, if the value's negative, then it's just going to flip it over. And then if that number happens to be greater than 1, it's also going to do the shrinking part. And if it's going to be between 0 and 1, it's going to do the narrowing. So, or the widening, sorry. Just to go back right quick. Yeah. If it's greater than 1, it shrinks it. If it's between 0 and 1, it stretches it. So break it into two categories. What's the value of a ignoring the sign? Is it between 0 and 1, or is it greater than 1? And then go, okay, well, is that one positive or negative? So let's say, so here's, well, I'll have it in a sec, but here's the original function. And notice what happens. So originally, if I plugged in 2, I got out 2. But notice if I come down to this function, when I plugged in 2 to f of x equals -2 times x, I'm down here at -4, which is exactly what you expect. It's -2 times the absolute value of x. So basically what it's saying is find the value for the absolute value of x, find that function, and just multiply it by -2. And that's going to work with any value. If I give you -1, like let's come over here. If I'm here at the point -1, 1, well, since the function that we're graphing is -2 times the absolute value of x, -2 times the absolute value of -1 is -2 times 1, which puts me down here at -1, -2. So, and you can see what I mean by the shrinking versus stretching. Because these they're getting to these values a lot faster, even if it's flipped over. This is kind of like closing this thing up because of that. So just keep the two little notes about if a is greater than 1, between 0 and 1, and also is the value positive or negative. Keep those in mind. Those will come in handy for these not translations, but these stretches and flips. Now, this one is kind of interesting. It shows up every now and then. But the greatest integer function. Basically, what it does is, what's the largest integer less than or equal to x? So basically, you can some people refer to it as a floor function. Sometimes this is the floor function. And instead of seeing it written as these like fancy brackets, sometimes you'll see it written like this. F of x equals this, where you have like kind of just indicating, basically, I won't say chop off the decimal, because notice for -2.9, because it's basically rounding it down to the next, or to the closest integer. Negative 2.9 rounds down to negative 3, because negative 3 is the smallest number below negative 2.9. Now, there is another function that's called the ceiling function, which does the opposite. So the ceiling function, it looks like this, which is literally just turn the floor function upside down. And if we were to test these values, so f of 4.3 for the ceiling function, that would be 5. So this one just rounds up. And then f of negative 2.9 would be negative 2, because remember, when you round up with negative numbers, if I'm saying what's the largest integer above negative 2.9, because remember, if I have negative 3 or if I have negative 2, you're talking about how close is it to 0 for the negative value. So negative 3 is farther away from 0 than negative 2, and thus it's going to be, negative 2 is going to be larger than negative 3 by that logic. And some people sometimes call it a stair-step function or a staircase, because notice it doesn't matter any value between 0 and 1, not including 1, just rounds back down to 0. If I have 0.999 and I take the greatest integer function of that, that goes straight to 0. Things like that. And then last thing to cover today are piecewise-defined functions. Now, a lot of people don't like to deal with these, mostly because there's just a little bit of complication with them and kind of reading them. But basically, piecewise functions, so it's terms of two or more formulas, each valid for its own unique portion of the real number line. So, for example, here's a good example of a piecewise function. It's the line negative 2x minus 2 if x is less than or equal to negative 1, but it's x squared if it's greater than negative 1. So here's what I'm going to do. I'm going to indicate the first part is this kind of cyan light blue color. So notice I have to be less than or equal to negative 1 for this to work. So here's negative 1. So let's plug in f of negative 2 just to get a value. Now, because I'm less than or equal to negative 1, I use this function in my evaluation. So I do negative 2 times negative 2 minus 2, which that's going to be positive 4 minus 2, which is positive 2. So here's negative 2, and I'm here at positive 2. Let's do another value. Let's actually do negative 1. So if I pick f of negative 1, this says if I'm less than or equal to negative 1, I need to be using this function. So we'll plug it in again to that function, because negative 1 is definitely less than or equal to negative 1. And so if I plug that in, oh, I plotted that one wrong. You've probably been yelling at the screen. It should be negative 2, positive 2. And then this one should be at negative 1. It should be 0. Now I do have another option. I could pick negative 3, negative 4, something like that. But remember, you only need 2 points to make a straight line, so I've got my 2 points. But one other thing I need to take into account. It's only the negative 2x minus 2 line to the left of negative 1. So if I can draw this correctly. Close enough. I don't include anything to the right of -1 from here. Reason being, piecewise function says this one literally draws the line at -1. I have to separate it out as everything less than or equal to -1 and everything greater than -1. So let's work on that now. Let's use red, so these are very distinct. And so if I do f of 0, that one's pretty easy. 0 squared is just 0. So I get that value. If I do f of 1, I get 1. F of 2 is 4. You get the idea. And then f of 3 would be 9. I think this is a 10 by 10 graph. Technically 20 by 20 because it goes in each direction, but 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So does like that. But right now I've only got it graphed at 0 into the right. So I still need to take into account this -1 part. And what I'm going to do there is I just need to know what is -1 squared. Or I should say, what does -1 squared equal? Well, that one's easy. -1 squared is equal to 1. But when I plot this point, remember we talked about included and excluded and things like that. So in reality, this domain is actually -1 to infinity. And this domain is -infinity to -1 included. So I'm going to use that to my advantage in graphing this. So at -1, if I was using the function x squared, at -1, I would be at 1, so I would be here. But to indicate that this point's not included, we're going to keep that parabola shape, which we know from before, and then we're just going to connect it with an open circle. And so that gets us all the values we need for this. And so whenever you graph a piecewise function, you always need to look at, okay, what values are included, what values are excluded, and what's my interval that each of these functions is working on. And if it helps you to write the x is greater than -1 as -1 to infinity, if the interval notation helps, write the interval notation. If it doesn't help, you don't have to write it. Just write whatever helps you solve the problem. But the key takeaway is going to be find where the point where these are going to meet, which is typically your boundary point. -1 is this division. So, and then I look at this and go, okay, x is less than or equal to -1. Okay, so I need to always be dealing with this function if I'm less than -1. And then if it's greater than -1, I get to use this function. And you can see here, that's exactly what we've done. If I'm to the left of -1, I'm on the function -2x minus 2. If I'm greater than -1, but not including, that's what that red open circle's there for. I've just got my standard x squared parabola. So just break it down piece by piece, and that will really help out with piecewise functions. And so that does it for the first lesson, and we'll pick up with 3.4 next time.